Okay, so I just want to say a quick kind of technical note about how we can actually derive this. So we like this kind of expression because it's basically saying so we like this kind of expression because it's basically saying the universal property for the coproducts. It's basically saying that if we have this M, it's basically saying that if we have this M and U is, it's basically saying if we have this arrow M from A plus, it's basically saying if we have this arrow M from A plus B to C and M after the left injection is U and M after the right injection is V, then that M is equal to our match function, our kind of what should be this unique intermediary arrow. And indeed, this is what this result says. But there's a question of how can we actually obtain this rule here, because we had this kind of previous version of the rule where, if you recall, because we had this sort of previous version of the rule where these red and purple expressions weren't here up above, and these U and V were replaced with this and this respectively. So if we had that rule to begin with, how could we sort of derive this sort of more intuitive kind of rule? And the answer is that we can basically use this rule up here. So this is something I haven't mentioned yet explicitly, but this is basically the rule for alpha conversion involved in sum types. And basically the idea here is that in this match function, we have these kind of bound variables. So X gets bound to U and Y gets bound to V. And it doesn't really matter what those variables are called. So if we can sort of change our term, so in particular, if we can change U to a term U dash by replacing, so in particular, if we can change U into U dash by replacing every X with an X dash, and then we can sort of replace this U with X bound to it, with U dash with X dash bound to it. So basically just changing the variable. And then that won't affect the nature of this arrow. And similarly with the Y's and the V's. Okay, so that's what this rule says. I ran out of space, but I meant to write these two expressions above the horizontal line. So this is the kind of alpha conversion principle for the sum types, and it's basically telling us that this kind of match function just sort of really depends on thinking of these things as functions, and it's not really sensitive to what we call the bound variables. But anyway, we can look at a special case of this kind of alpha conversion rule. We can really look at the case where X is equal to, we can really look at the case where X is X dash and Y is Y dash. And what this is then saying is something quite obvious, which is that if U equals U dash, then the match that we build using those, and in that case where, so we can look at a special case of this kind of alpha conversion rule when so we can look at a special case of this alpha conversion rule when X is X dash and Y is Y dash. And what it basically says then is just that if U equals U dash and V equals V dash, then the match that we build with u and v will be equal to the match that we build with u dash and v dash. And that's kind of what we want to get this kind of rule here, okay? Because we can imagine our original rule written down, and that would be like match of s comma blah 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 equals m. And then we can also get that if we're assuming this and this, then match of blah blah blah, what used to be here, can be shown to be sort of equal to this expression, okay? Because we can sort of, once we show that these u and v that we're building with are equal to the kind of expressions that were there before, some version of this allows us to say that the whole match thing that we build using these new u and v's is equal to what was there before. And then we can just use the sort of transitivity of equality to obtain this kind of result. So that's it. That's how we get this universal property. I should also mention, while I'm here, that there's another alpha conversion principle for the function types, and it's very similar. Basically, all it's just saying is that it doesn't really matter what we call these bound variables. You can replace the bound variables with one name, with another name, and instead of sort of having a lambda x, you can have a lambda y. And if you do it properly, the functions you get out will end up being the same, okay? So it's similar to the way, in standard mathematics, we might have the integral of x squared dx is equal to the integral of v squared dv. It's just a change of bound variable. It doesn't really affect the way that these things evaluate. So if you think about this in terms of, it's really just this idea that we can rename bound variables. And we have a similar thing going on in sort of calculus, right? These two things are equal because the kind of x here gets bound by this integration. And if we renamed everything, and if we renamed all the x's as v's and we evaluated, we'd get the same result because it doesn't really matter what we're calling these bound variables. And it's similar here. If we have this sort of b dash that we get by replacing every x with a y, then the function where we use a y, and then the function where we replace every y in b dash is the same as the function where we replace every x in b.